Vanden, and today I'm going to be presenting 3D depth detection using integral imaging and computational volumetric reconstruction. So a little bit about me. So I'm an electrical engineering major at the University of Hartford. I'm part of the class of 2026, and I started this research in fall of 2022. So a quick overview of what I'm going to be going over today. So I'm going to start with a brief intro to what integral imaging technology is. Then I'm going to move on to what volumetric reconstruction is and some of the image comparison methods we use. Then I'm going to talk about the depth estimation methods. So we have brute force, which is the conventional method. Then we have polynomial curve fitting and spline curve fitting. And finally, I'm going to talk about a graphical user interface I created. So part one, intro to 3D integral imaging technology. So integral imaging technology allows for 3D images to be processed and displayed without the use of 3D glasses, using several cameras with different viewpoints that are combined into a final composite image. There are many applications of integral imaging and fields that it can be applied to, including medical sciences, robotics, and surveillance. And applications include 3D modeling of objects, 3D displays, and what I've been working on, which is depth detection. In figure one, right here, a pickup stage can be seen. So we can see that we have several different cameras, all that have a slightly different view of this 3D scene. In this case, it's dye. And so each of them are going to have a slightly different view. The other application that's shown here is a lenslet display. So here, each of the elemental images have their own lenslet, and then they are passed through this lenslet, and they combine into a final reconstructed 3D image. So what I specifically have been working with is volumetric reconstruction. So in order to perform depth detection, I've been using volumetric reconstruction. This involves using a virtual pinhole array, shown in figure one over here, in which a bunch of elemental images are reconstructed into a final reconstructed image at a specific depth. So this specific depth is z away from the pinhole array, and the final image can be described by this equation. In figure 4 here, you can see one of our elemental images. So this is one of the original images we picked up when we set up the equation, or when we set up the camera setup. And then we can run it through our image comparison method, image reconstruction method, and we can reconstruct it at different depths. So here in figure 4b, we have it reconstructed at the depth of the car, and in 4c, we have it reconstructed at the depth of the bus. And one of the features of volumetric reconstruction that I'm not going too deep into, but it is pretty cool, is that it's actually able to see past some of the obstructions, because each of the original cameras of the elemental images has a slightly different view of the target, so they can be reconstructed and basically stitched together. So I used two different image comparison methods. One is the structural similarity index measurement, or SSIM, and also the peak signal to noise ratio method, or PSNR. So the SSIM method takes 11 by 11 blocks of the original elemental images and 11 by 11 blocks of the reconstructed image, and finds the variance between these two images. So in MATLAB situation, or in MATLAB, which is the specific application we're using, they're 11 by 11 blocks, but they're not always this. It depends on what exactly you're using and what you have it set up to do. And then peak signal to noise ratio, this finds the maximum ratio between the signal and noise of an image. So that allows us to quantify the quality of a reconstructed image. So then we can move on to depth estimation methods. So here's a quick flow chart of what the code that I programmed for depth detection is. So first we're going to have a set of elemental images. Then they're going to be ran through our volumetric reconstruction method at several different depths with constant steps in between those depths. Then we're going to put them into the image comparison method, so the SSIM and PSNR, and that is going to give us our best reconstruction plane, or the distance the element is from the camera. So, brute force depth detection. So this is the conventional depth detection algorithm. It essentially involves reconstructing at every possible depth. So in this example, we have a object that is between 500 and 2,500 millimeters. So we want to determine the depth of the object within 1 millimeter. So what we do is reconstruct at 500, 501, on and on to 2,500. So this, in computer science, would be most closely to a linear search, where you're checking every possible element to see what the best match is. However, this method is very slow. So for this data set, which is the 5x5 road sign data set, it took around 80 minutes to detect the peak with an accuracy of 1 millimeter. So here in figure 9, you can see the elemental image. So this is the road sign. Then we can put it into our reconstruction method. So I've reconstructed it at every depth. But here we have 500 millimeters. So right here it's very blurry, and this represents the very start of our graph. Then at 1482, which that is where it's the clearest possible image. So that's going to be the peak of our graph right in the center there. And finally at a reconstruction depth of 2,500 millimeters, which is at the very end of our graph over here. So you can see that the method, or the reconstructed results go up to their maximum at a depth of 1482 millimeters before going back down again. So here is the experimental results from the brute force. So here we have our elemental images, and you can see that it's just iterating slowly through, and every image has a slightly different view of the sign. And then over here, we have our reconstructed images. So you can see right now, it's slowly getting better, less blurry, until it eventually reaches a minimum blurriness at 1482 millimeters, and it goes blurry again in a second. Yeah, right now. So, the first method I try to apply to reduce the time this takes is polynomial curve fitting. So the MATLAB polyfit function generates coefficients of a polynomial of degree n, as shown in this equation, that best fits a set of data. The best fit polynomial represents the curve of the reconstruction planes here, and the peak of this curve is going to represent the best reconstruction plane for that set of images. In figure 12, this can be seen with the polyfit method with a range of between 500 and 2,500 images, and we had to do 24 divisions with a polynomial of 8. So initially, I believed that simply increasing the number of polynomials would make it more accurate. However, this isn't exactly true. So initially, it started off pretty accurate with a inaccuracy of around 100 between 100 and 20 millimeters. However, this quickly increased. So, quick definitions here. So time, that's just the time it took for the algorithm to run. The difference, so that is the difference between the actual reconstructed plane and the detected best reconstruction plane. And extra peaks, that is the number of extra best reconstruction planes detected. So here we can see that initially it starts off very accurate, but then once we increase to a certain point, it quickly goes to an accuracy, or a difference of around 1,000 millimeters, which in a range of 2,000 millimeters, that's not really accurate. So what is the reason for this? So the reason for this is because of over and underfitting. So underfitting occurs when a polynomial is not complex enough to represent a data set. So here you can see I applied a linear curve to our data set, and you can see that it doesn't match our data at all. It doesn't even intersect with a majority of the points, or even, it's not even near a majority of the points. Overfitting, on the other hand, occurs when a polynomial is too complex to represent the data. So while it may exactly represent the data at the specific points that we give it, it's not going to, outside of those exact points, it's not going to be accurate at all. So you can see here, while it does exactly go through all of our points, and they're actually shrunk down, because if you look at the scale of the graph, they're shrunk down because the polyfit function at this step spikes way up, nowhere near our data, or nowhere near where we'd expect the best curve to be. So the next idea was to keep the number of degrees constant at 1 plus the number of objects in our image. So with this, we got a lot better method, or we got a lot better results. So and we changed the degree, and what we were changing between these tests is the number of degree, or the number of reconstructed images we're giving the polyfit algorithm. So here we can see that the time increased linearly, which we would expect because the reconstruction is doing more and more depths. So we'd expect when it does one more depth reconstruction plane, it's going to increase by approximately whatever the time it is to reconstruct one image. So, but the difference actually remains initially it's all over the place because, well, initially it's trying to get the best depth from 2 reconstruction planes, which really isn't that good of data, but eventually it evens out around 100 millimeters. And the number of extra peaks detected is 0 because when we have a polyfit, or when you have a polynomial function with only 2 degrees, it's only going to have 1 peak. So the number of extra peaks is held at 0. The other curve fitting method we used was spline. So the MATLAB spline function returns a piecewise polynomial function that perfectly represents the data points. So the data is divided into sections in which cubic polynomials are applied to them. That perfectly represents the data, and then all these individual sections of data are combined together into a final curve. So the spline will exactly fit our data points. So when we use the polyfit function, the line didn't pass through all the data points exactly, while here it will pass through all the data points exactly. And the peak of the image we would expect to be where the best reconstruction plane is. So here, much like the polyfit with a change of 2, our time increased linearly because we were increasing the number of reconstruction planes, but the difference was significantly lower. Initially, it was all over the place because it did not have enough data to be able to accurately create a curve that represents the reconstruction curve. But eventually it settles down at a difference of around 25 millimeters, very close to the actual depth of the object. But the extra peaks, unfortunately, does not remain constant or remain at 0 because when you're applying a curve to a couple of sections, occasionally it'll go up and then down again, which would give us extra peaks. So when comparing these two methods, we can see that there was no significant difference in time between the two methods, though the polyfit does take slightly longer when you give it more data points than the spline method. However, the real difference can be, or the real change can be seen in the difference graph, where the spline is significantly lower than the polyfit once it's able to get an accurate bit of data. However, the only issue with the spline is that it gives extra peaks that we would need to write some code to be able to basically eliminate these extra peaks and determine which is the true correct peak. So the polyfit function, while it's not going to produce extra peaks, it does risk, you do risk over and underfitting the data, and it's generally less accurate. The spline, on the other hand, needs less info, so you don't need the number of objects in the image when you're performing the reconstruction. and it's more accurate, but it may produce extra peaks that you need to write software to get rid of. So the next part was creating a graphical user interface. So the goal of the graphical user interface was to reduce the knowledge of coding and volumetric reconstruction needed to, or the knowledge of integral imaging needed to perform volumetric reconstruction of 2D elemental images. And in addition to creating the graphical user interface, the classes were made which would make it easier to perform volumetric reconstruction in the future with more complex applications. So here is our parameters. So here's where the user enters the basically the camera setup parameters. And here is the actual page where they perform the reconstruction. And I'm actually going to perform a quick technical demonstration of this. So here we have a data set which it is basically a cup behind a very heavily occluded or a very heavily occluding plant. So you can see that each picture has a slightly different view of the cup, and in this data set there are 100 images in total on a single plane. So in the camera parameters, we're going to just give it the input directory of these elemental images, the focal length of the camera, the size of the camera sensor in the X and Y direction, the number of cameras in each direction, so this is a 10 by 10 data set, 10 by 10 by 1 data set because it's single planar, and the shift between the cameras in each direction. So in this setup, each camera had there were 10 millimeters between each camera. So if we want to perform range reconstruction, we're just going to need to quickly give it an output directory. So that's just where it's going to temporarily save the images so that we have them. And then we're going to need to give it the minimum. I know in this setup that all the objects are between 500 and 2,500 millimeters. So I'm going to set the minimum to 500 and the maximum to 2,500. And I'm going to reconstruct at depths of 250 millimeters. I'm going to run the reconstruction. This is going to take a little bit. I estimate around 30 seconds. So, yes, hopefully it works pretty quickly. That's the only thing with reconstruction, which is why I've been trying to generate this using the polynomial curve fitting and spline curve fitting. Is it is extremely slow, so to run the reconstruction algorithm. And while it can be sped up, there's limits to how quickly it can be sped up. So we want to generate a method that's it doesn't need to do every possible depth. It only needs to do a handful of depths. So double check that it's running. It is running. It's running very slowly.
Are you running it on the Dana 321 computers or your computer?
The Dana 321. And it's completed. So you can see that this particular reconstruction took 53 seconds, which you'd actually want even more steps. This was, it only did it only did like 8 images here. So you can see that it's really slow, that 8 minutes, or 8 depths took around a minute. So you can see that it slowly zooms in as we go through it. So here you can see that the plant is in focus. So the plant is around 750 millimeters away from the camera. And as we continue through, we can see that the cup is now more in focus. It's really hard to tell on this computer, on this projector. The cup is more in focus than it was in the other images. I can actually hold up and make it a little bit bigger. There we go. That's a little better. So you can see now the plant's in focus, and now you can see the cup more clearly. Alright. So in conclusion, so overall, between the curve fitting methods that I applied, spline was the preferred method due to its accuracy. However, neither of these methods are capable of true depth detection. They can't get the exact depth. However, what we can do is use this predicted depth and then apply our conventional method, which is able to accurately get the depth at a few basically it runs a reconstruction plane using the conventional method, which gets it at smaller increments, but we don't need to do that for the entire range of the data. So we could use this method in addition to the brute force method to speed up this process. So I'd like to take a second to quickly acknowledge the Faculty Senate and Student Affairs Committee for the University Scholars Program, the SETA Student Engagement Grant, the Honors Program at University of Hartford, my advisor, Professor Shen, and all the members of Professor Shen's research group, especially Nathan and Gilad. Thank you.